Hi guys, welcome to my YouTube channel. This is the second video that I'm recording. In this lecture, I want to talk about an application of Reconfigurable Intelligent Surface in the wireless networks. This is an outline to this lecture. We first review some of the fundamentals of the first presentation. Then we go to the physical layer security, which contains passive eavesdropping and active eavesdropping. We introduce a system model for this specific project and investigation. Then we investigate a method for channel estimation in the IRS-assisted wireless networks. Then we introduce active pilot attack, downlink data transmission, achievable secrecy sum rate, pre-coding and phase tuning, which is the optimization phase. And we propose an iterative algorithm, the result of the simulation, and finally the references. Okay, we first review some of the fundamentals of the first presentation. This is an reconfigurable intelligent surface which consists several elements, for example, dipole elements on its surface. In the background and in the background surface we have a copper plane, and behind it we have a control circuit board which is connected to an IRS controller which tunes the phase shifts of the elements, and the IRS controller is connected to an access point or base station via a backhaul link, wirelessly or wiredly. The elements of the reconfigurable intelligent surface can do many kinds of actions: reflection, refraction, absorption, and focusing. And as I said, the main focus are work and in researches in many industrial working, is focusing this incident signal to a desired angle and position. It is a beamforming by tuning these phase shift of the elements and focus the incident signal to an intended angle. It has some challenges using reconfigurable intelligent surface in the wireless networks. First of all was reflection optimization, which was a jointly designed optimization problem. In many cases, it resulted in non-convex and NP-hard problems. Channel estimation was a second challenge due to the lack of RF chains on reconfigurable intelligent surface, which was a good thing actually. And the final challenge was the deployment. In this lecture, actually, we covered the two first challenges, which are the most important. And we had a system model here, which YK was the, in the multi-user case, YK was the signal transmitted from this access point to the K users. HRK is the channel between the IRS and user K. Phi is the diagonal case of the phase shift of the elements of the IRS, and G is the line of sight channel between the access point and IRS, which is constant for different elements. It's similar for the different elements of IRS. HDK was the direct channel between the user K and the access point. And WJ is the pre-coding vector which the purpose of using that is, for example, reducing interference or quality of service things and these things. SJ was the original signal that is intended to be transmitted from access point to user K, to user J actually, and NK is the noise term. Signal to interference plus noise for user K is written here, and we said that HK is named effective channel or cascaded channel in IRS-assisted wireless networks, which equals G multiplied by diagonal case of the HRK Hermitian. This channel is the effective channel. Okay, and we said that IRS doesn't perform the amplification of the signal and just reflects the incident signal, and theta n can be, which is the phase shift of the elements, can be between 0 and 2 pi, and also it is more practical to be assumed discrete. For example, 8 levels between 0 to 2 pi, and with 8 points we said that we need 3 pin diodes on each element. We had some problem formulation with the assumption of perfect CSI and unknown CSI, which in this case the purpose is channel estimation, and in this case we have some optimizations, for example rate optimization, energy optimization, SINR maximization, and security enhancement, which in this lecture we investigate and deep into the security enhancement case. And in the channel estimation we had some techniques, which the most basic one was on-off method, and in this lecture I will explain that as an introduction to the active eavesdropping in the IRS-assisted wireless networks. And IRS had some applications in other technologies such as UAV-assisted IRS system, NOMA system, physical layer security, and these things. Okay, as an introduction, I should first introduce you to passive eavesdropping, which an eavesdropper comes into the cell and network, and by using the public pilots in the network, it is public and everybody can have the pilot signal, which is used in channel estimation. Use these pilot signals, and the received signal from the access point is decoded by these pilot signal. Is decoded, I mean the eavesdropper can do the channel estimation between the access point and itself, and by the channel estimation it can, by having the actual channel, this channel HAE, it can decode the signal and have the information which was intended to be received just by this user. So an eavesdropping is happened here. So by IRS we have more degrees of freedom and can suppress this eavesdropper in the network and enhance the physical layer security of the system. So the goal here is jointly design the phase shift of IRS and the precoding scheme, which is done in access point, to maximize the achievable secrecy throughput. But we have another phenomena which is more harmful to the system, and it is called active eavesdropping versus passive eavesdropping, which I already explained. Okay, in passive eavesdropping we have secrecy for free property of MIMO systems with large antenna arrays. In 5G system, which we use the MIMO system, MIMO technology, by eavesdropping, let me so if this is the base station with some antennas, and this is user 1 and this is user 2. So previous to the MIMO technology, the base station radiated the intended signal for user 1 in 360 degree. It was the omnidirectional antennas which radiated the signal in all directions. But in MIMO systems, the base station can beamform the signal to the intended user. So instead of radiating the signal in all positions, for the signal intended to be received by user 1 can be beamformed just for itself. So the intended user for user 1 is not received by user 2. So this is a good point here. And also we use less energy here. So instead of radiating the signal in all directions, we just radiate the signal in just one angle and within specific bandwidth. This is the bandwidth of the beam. So if an eavesdropper, passive eavesdropper is here, it cannot eavesdrop the signal which is transmitted to user 1. So for eavesdropping, the eavesdropper should come here in the direct way, which between base station and user 1. So it can eavesdrop the radiated signal with the public and known pilot signals. So this is a good thing in MIMO system, which an eavesdropper for eavesdropping, the only way for eavesdropping is to come between the user 1 and the base station. And also no need to know the presence of malicious terminals. But in active eavesdropping, active eavesdroppers are not suppressed automatically. Attackers can contaminate the estimated CSI. Non-vanishing leakage to the active eavesdroppers, attacker CSI has to be known for suppression. And in the active eavesdropping case, this is the base station, and it is user 1, user 2, and eavesdropper. Okay, even with using MIMO technology and beamforming technology, for example, this base station before existing of active eavesdropper here, the base station radiates the signal to just user 1. Okay, this is ideal and everything is good. But with existing active eavesdropper in the system, it can contaminate the CSI which is calculated by the base station. So the eavesdropper sends an active signal, an active attacking signal to the base station and contaminate the channel state information. So the channel estimation for user 1 is calculated incorrectly by the base station. So instead of just sending signal to the user 1, it also sends the signal to the active eavesdropper. This is the point in active eavesdropping. By contaminating the CSI calculated by the base station, instead of just sending the signal to just user 1, it also sends it to active eavesdropper. So the active eavesdropper has the information which was intended to be received just by user 1. So when eavesdropping has happened here, this is a bad thing. So in this project and in this research, we intend to suppress the effect of these active eavesdropper in the system with reconfigurable intelligent surfaces. Is there a tractable way to make active eavesdropper partially blinded here? Yes, it is. System model here. In downlink, signal overheard by an active eavesdropper has access to the transmission codebooks, the pilot signals. It is public. And in uplink, active attack in transmission cycles. That active attack by active eavesdropper to the base station to contaminate the CSI and channel estimation, and consequently the base station also sends the signal to the active eavesdropper. Okay, if this is a base station, this is user K, and this is RIS. So, and also this is eavesdropper. This is the eavesdropper. So, the base station, if wants to send a signal to user K, it has one choice here, the direct channel. It has one choice to get through this way, sends a signal to the reconfigurable intelligent surface, and it is reflected to the user K by tuning the phase shift of the RIS and the precoding vector at the base station. And also the signal can be received by active eavesdropper, which previously contaminated the CSI and channel estimations done by base station. So the received signal at UTK, it has a direct channel, HK transpose is here, this channel, and X is the transmitted signal from the base station. YKR is this way, the signal which is received from these channels. AKT is this channel. Diac theta. Theta is the phase shift of the RIS, so this is that phi matrix. UT, U transpose U is this channel, and X is the transmitted signal. Okay, so AKT, diac theta, and U transpose is the signal which is received by user K. By substituting these vectors here and take theta out of diagonal case and put AK to the diagonal function, we have theta diac AK U transpose multiplied by the original signal X, and we call this channel the effective or cascaded channel, and it is called FK transpose. So and also the signal which is received by the active eavesdropper is a direct channel between the base station and active eavesdropper here, and also a signal which is reflected from RIS. So this is another channel which active eavesdropper can receive the signal, and this is the same as here. So this is the channel model, or specifically this is a system model. Okay, for channel estimation, the most basic technique is on-off method. On-off method is a technique that in each period of time, just one element of the IRS is on and the other elements are off. So at first all of the elements of RIS are off, and HDK, the direct channel between the base station and user K, is intended to be estimated. So the user K sends the pilot signals, and base station calculates the channel, the direct channel. So it is calculated, for example, by some simple and basic techniques such as least squares or LS, and also MMSE techniques. So the direct channel can be estimated here. With having direct channel, we just have one element of IRS on and the others are off. So if this element is on and others are off, user K sends a signal, sends an omnidirectional signal, because it has just one antenna and cannot beamform the signal. So one signal is received by base station through this direct channel HDK, and another signal is received by reflecting by this on element. So by having this HDK, this cascaded channel can also be calculated with that conventional channel estimation techniques such as LS and MMSE, by subtracting this effect of the direct channel from it. So this channel is estimated. So we take this off and take this on. Others are still off. So this channel is estimated, and continue this process until the last element, and it can also be calculated. The effective channel can be calculated. So we have all channels corresponding to each element calculated. So this is on-off method and is the most basic technique. But it is it takes some time and some proportion of the channel coherent time. So we would not have that much time to send the signals intended. Okay, as I said, the estimation of direct channel at first, direct channel while all of the elements are off, and just one element on and the others off, estimating the channel progressively until the last element. So active pilot attack here. Active pilot attack is at first is done while estimating the direct channel. This is the pilot signal corresponded to user K. This is the channel, and this is a signal received from user K and also the active eavesdropper. Base station for estimating the channel here by having this pilot signal and the orthogonality between the pilot signal. You know that mu K multiplied by mu J is 0 for K not equal J, and for the case where K equals J, it equals 0. It equals 1. So the base station, by having this pilot signal and the orthogonality between them, by multiplying mu K to this received signal, so mu K transpose multiplied by mu K conjugate, so this equals 1, and the remaining term is this HK with some coefficients, which by dividing we can neutralizing the effect of that. So HK is calculated for user K, but the active eavesdropper selects the user L for eavesdropping and stealing the information. So user L is the victim here, user L. So for user K, which is not equal to user L, the channel estimation is done correctly, okay? But for user L, which is the victim, the channel estimation here, HL, by multiplying mu L conjugate, can be obtained correctly here, but there is another term here, which it is mu L. In this case, by multiplying mu K by mu L, we have 0, because L is not equal to K. So the result is 0. But here we are working with user L, and the active eavesdropper is attacking user L as the pilot of the user L. So by multiplying mu L here, this term would be equal to 1, and another term, HE, which is the channel of the active eavesdropper, by some coefficients, is added to the estimated channel. So the base station, instead of this is user K, this is eavesdropper. So if the base station estimates the channel of L as this case, the eavesdropping would be like this, and eavesdropper is suppressed completely. But here we have HE. HE is the channel of the eavesdropper and between the channel between the eavesdropper and the base station. So by adding this channel to the estimated channel, the base station doesn't only send the signal to user K, but it also sends the signal to user E, which is the eavesdropper. So the eavesdropping is done, and the attack is complete. The eavesdropper reached success. So let me erase this. Also, in this case we had a direct channel, and in this case we are estimating the effective channel, which was here, the effective channels one by one. In this case, user L is still the victim. The received signal, this is the user K signal, and this is the eavesdropper signal. Also, this W here are pilot signals for the effective channel. This is for user K, and as I said, the user L is the victim, and the active eavesdropper selects user L to attack to. Okay. Here, also the orthogonality still is and still exists, and by multiplying WL to this term, the answer is 0, because K is not equal L. But for the case where the signal is for user L, by multiplying WL, it equals 1, and also this is 1. So we have two channels here for user L, and this is the actual channel, and this is the active eavesdropper channel. So again, instead of just sending the signal to user K, the signal is also transmitted to active eavesdropper. So the attack is also complete. In downlink transmission, X is the sum of original signals and precoding vectors, and also the transmitting power should be equal to PT and not more. The receive signal at UTK is like this. GK theta is the channel, is a channel for the sum of direct channel and the cascaded channels for user K, and this is the interference term, and also this is the noise. So the receive signal at UTK being formed by WK theta, the goal is suppression of the active eavesdropper. So by tuning this WK precoding vector for user K and theta of the IRS, we intend to suppress the active eavesdropper in this case. Okay, so achievable secrecy sum rate. This is the formula. SINR is the actual signal divided by the variance of the noise and the power of the interference terms. The unachievable secrecy rate for UTK is given by subtracting the information leakage to the eavesdropper from RK here. So information leakage to the eavesdropper. But it is difficult to characterize the exact information leakage. As an upper bound, we assume a worst case scenario, which is the eavesdropper is capable of acquiring its instantaneous CSI as well as cancelling the interference of other legitimate duties. RK for active eavesdropper is like this, and the achievable secrecy rate is by subtracting the information leakage from RK. So this term would be like this, and achievable weighted secrecy sum rate is like this. And this omega here is the weights for each user. Precoding and phase tuning. Optimal precoding vector and phase shift. By optimal choice, we do the optimization, which is maximization of secrecy sum rate. Secrecy weighted as this here. Secrecy weighted, achievable weighted secrecy sum rate. Okay. Maximizing this, but this is an NPR problem, which is a drawback. So we assume some assumption. We use match filtering for WK. Another assumption is that base station knows the existence of the active eavesdropper and no access to the active eavesdropper's instantaneous CSI. So the optimization problem would be a stochastic form of secure, regularized, zero forcing precoding. Okay. The optimization would be like this: minimum of sum of GK theta, which is the sum of the direct channels and effective channels, multiplied by WK minus 1. So we like to for user K, we like it equals 1. It gets close to 1, and for other users it equals 0. And also this term for active eavesdropper should be less than an epsilon term, which is a small number. But we have no access to instantaneous CSI of the active eavesdroppers. So we do the stochastic optimization here by taking the expectation term from them. So this is a stochastic optimization, and we first should calculate the expectation terms and then solve the optimization problem. By assuming these channel models here, HK, U, and AK, we can calculate the expectation here by using these channel models here to reach this term, which in the next video I just do the mathematics of this part and obtain this term, as I said, in the next video. Okay. So it will be calculated and investigated thoroughly. After that, after calculating this term, we should solve the optimization problem, okay? But as I said, WK and theta are coupled together. So the optimization is non-convex. The optimization is non-convex and should be solved by some techniques. Here, by alternating optimization, we can separate the parameters which are WK, I mean pre-coding vector at the base station, and also the phase shift of the IRS. So we can separate them in the optimization and optimize them separately. So it would be a convex problem. We do this process in iterating manner till the convergence happens. Alternating optimization is an iterative procedure minimizing or maximizing the function fx equals fx1, x2 to xt jointly over all variables, alternating restricted minimizations and maximizations over individual subsets, okay, of variables x1, x2, xt. So instead of just jointly optimize them together, we optimize the problem over individual subsets of x1, x2, xt. For example, x2 to xt is assumed fixed in an iteration, and just x1 is the variable parameter, okay, and we just optimize x1. In the next iteration, we just optimize x2, and in this iteration, we just optimize xt. In the next iteration, we get back to the x1, we optimize x1 while others are fixed, and we do this process again and again till the convergence happen, okay. This alternating optimization method is the basis for Siemens clustering algorithms, many forms of vector quantizations, expectation maximization, or EM algorithm for normal mixture decomposition. 4 reasons why alternating optimization may be preferable to its competitors. 1. This division of variables, which explicit partial minimizer formulas exist for most of the variables. Computationally cheaper, it is very important here. Computationally cheaper than the best standard optimization approaches in some cases. These computationally cheaper algorithms are so important for us. Saving of development time with good convergence, more adapt by bypassing local minimizers than other approaches. When you have a non-convex function, this is a non-convex function. This is a convex function, for example, which has just one minimum, but here we have many local minimums, here, here, here. So the algorithm for solving this non-convex problem should bypass the local minimums, okay? For example, if the starting point is here, it shouldn't get stuck in this local minimum because the minimum is here and it is so far away from the absolute minimum, okay? So the algorithm should be that powerful to bypass this local minimum. By bypassing, for example, gets here, then here, then here. Also, it is ideal to bypass this local minimum also. It is ideal to get stuck in this local minimum, okay? And alternating optimization is capable of doing this thing. More adept at bypassing local minimizers than other approaches. So this is a very good method, and it is widely used in researches. Another techniques which we should use to solve that optimization problem is semi-definite relaxation, or SDR. In SDR, remember that we had a constraint in the optimization, which theta k should be equal 1k is 1 to m. M is the number of elements of IRS, okay? So the phase shift, the absolute, the magnitude of the phase shift should equal to 1. This is because we assume that IRS doesn't amplify the incident signal and just reflects it, okay? So the amplification coefficient is 1. This is a constraint here, but it is called unit modulus constraint, and it is non-convex. It is non-convex, but with relaxation we can transform it to a convex constraint. By relaxation we can transform this constraint to this constraint. This is a convex constraint and can be utilized in CVX tool in MATLAB, and the problem can be solved. But when the result is obtained, we should take it to a feasible set. For example, we can divide k star. This is the optimal answer, which is obtained from CVX2. We can divide the result by this term. So the final answer is equal to theta. So it satisfies the constraint. Okay, this is the SDR approach. I have another example here, which is real valued homogeneous QC/QP problem. Suppose we have we want minimum of xt cx subject to xt aix greater than bi. Okay, we can have this is 1 by 1. Okay, this term here. So it is equal to the trace is equal. So we take this x here, or this x here. Okay, xt, and we define this as a capital X cx. Okay, as here. So this term as well, trace aix greater than bi, and x, which is the multiplication of x by x transpose. So it is positive definite. Okay, it is positive definite, and we add another constraint, which x should be greater than 0. So it should be semi-definite matrix, and also rank x should be equal to 1 because we multiplied x by x transpose, so the rank would be 1. Okay, so another constraint is added here, but the rank constraint is always non-convex. Okay, it is non-convex, and we relax it with this SDR technique. We remove this constraint here because it was non-convex. It is removed here. So this is a convex problem. We solve it with CVX in MATLAB. But what is the issue when using SDR? What is the issue? when using SDR. Converting the global optimum solution into a feasible solution. As I said, after the answer is obtained, we should convert it to a global optimum solution into a feasible solution, a solution which the rank, which is rank, should be equal to 0. For that, we have, for example, rank K approximation of a matrix A. Express A as a list of its ingredients ordered by importance by some techniques like SVD PCA. And then keep only the K most important ingredients. In this case, which rank X equals 1, we should keep only just the most important ingredient, okay? And the resultant answer has rank 1. Even with a feasible extracted solution, it is not an optimal solution. An NP-hard problem is solved in polynomial time. So SDR has some trade-offs, and we can use that depending on the optimization problem. The final iterating algorithm, intractable optimization problem, the objective function is non-convex and unit modulus constraint. The objective function is not convex, we solved it with alternating optimization, and unit modulus constraint, we solved it with SDR technique. So this is the SDR that I said. Instead of this constraint, we assume this constraint and solve the optimization problem and then convert it to a feasible solution. Project the solution onto the unit circle. This is a unit circle equals to 1. The magnitude, it means convert it onto the unit circle. So the algorithm would be like this. Until the convergence happen, do the process which assume C is fixed and C is that precoding vectors, okay? And we want to optimize phase shifts. These are fixed, and we just optimize this phase shift. After the answer is obtained, in the next iteration, we assume theta is fixed, and we optimize C or precoding vectors till the convergence happens, okay? The results would be like this. Proposed scheme, we see that using reconfigurable intelligent surface, we can increase achievable weighted secrecy sum rate compared to the benchmark, okay? So these are references and the actual paper which this presentation was based on is the 66 reference. Secure transmission is in IRS-Assisted MIMO system with active Eavesdroppers. Okay, this is the basic. This is the basis of this presentation. Thanks for your time and attention. You can contact me here.